Well, you can ask everybody. What? Hi.
Yeah, I would think it's like they're, yeah, sort of, yeah.
Yeah. So make sure from the homework, if you're gonna do it, do questions 3 and 4. No, 3 and 4. Okay, the stuff with Jordan form and the tableau. Uh, make sure you do, because we did question 1 here, the short theorem. So just reference that. And I don't know what was question 2. Yeah, I don't know. What was question 2? So hard to get. Question 2 was. Yeah, yeah. I mean, not all. Yeah, okay. Yeah, you should do, but mainly do. I don't know. I mean, you should be able to do problem 2. It's like previous stuff. But definitely do 3 and 4 so that if you have questions, I can talk. So please make sure you do 3 and 4 so that you understand the material. Okay. All right. So yeah, we're gonna do this today. We're gonna continue Monday. Yeah. Okay. So last time we left off in this example. We had this nilpotent map n and over here, and it has this signature 356, meaning the dimension of the kernel is 3, dimension of kernel on the square is 5, and 3 is the nilpotency. And I want to show you how to generate the basis for these vectors. So let me do it here. I also talked about it on Piazza. So the question is, why start with these 3 vectors, v1, v2, v3? So let me explain how you build the cycles, okay? Let's do it once again. building this basis. First, you find the basis for the kernel. Okay, in the book, he calls them eigenvectors. Do you know why they're called eigenvectors? Why the basis for the kernel of n are eigenvectors? Is the only eigenvalue. Is that okay? From the midterm? Yeah. So the only eigenvalue nv is equal to lambda v if and only if lambda is 0 for this guy when you're nilpotent. Okay? That was in the midterm. Okay. So let's do that first. So namely, you have to show the system of x1 to x6 equal to 0. Can you tell me which xi would be 0? X equal to what? 0 from this, using this. You guys think? Can you give me with your hands x? Yeah. X equal to what is 0? What index will I put? What? No, x1 to x6. Yeah. Yeah. And then, well, you can use your fingers, like there's like you have 10 fingers. Yeah. Okay, so we have the one guy, wait, did you say 5? No. Oh, wait. I think you're right. No, you're not right. No, 6 is not the. Do you guys understand how this works? So you map it. And then you set them to 0. So like x1 is 0, x2 is 0, and x4 is 0. Is that okay? Is that okay? Is that okay? Okay. So the basis so the kernel of n would be given by the span of the remaining guys. So x3 survived. Let me just say E3, okay? E3 survived. E5 survived. And who else? E6. Okay. So this guy survived. So this is where you start. So here's how you play this game. It's like a game. So we want to generate the basis. Like I said, n v1, n v1, v1, n v2, v2, and v3. So here's how you do it. You start with this basis and you go backwards. So let's do it slowly. So first you have to solve n of x equal to E3. Okay? So I'll explain why. Let me solve it first. So this is 0x1, x2, 0, x4, 0 equal to 0, 0, 1, 0, 0, and then another 0. Okay? Can you tell me which like which guy is 0 and which one is 1? Yeah, you can say fine. Yeah. So x2 is 1, x1 is 0, and x4 is 0. Okay? No, we haven't done, just wait, we're building this. I'm saying how to build it. You asked this last time, how I build it, so I'm building it. Well, just wait, you'll see. One thing at a time. So Therefore, X, anyhow, so you get from here the following. The solutions to this system are the guys that die out. Where am I? Yeah, so X3 survived and X5 survived and X6 survived and X2 became 1 always. So this is fixed. So let me write this as real number. This is good because it's confusing. So these are arbitrary, okay? Because we didn't touch them. They can be anything. So the solution to the system is this, guys, with a 1. But just to make your life easy, just pick one of them, okay? Just take the E2, right? So you get E2. Now, solve it again. Nx equal to E2, all right? So let's do this again. So this is the system 0x1, x2, 0, x4, 0 equal to 0, 1, 0, 0, 0. And from here you get that who is 1? Yeah. And x2 is 0 and x4 is 0. So from here, again, you have a system. X3 can be anything, X5 can be anything, X4, no, X5, yeah, X6. And X1 is 1. So again, you just pick one guy. You just need one because you can have a span. Okay, so you put E1. All right. Now let me explain what has happened. I just built the first cycle. Okay, so let me explain how that worked. We'll go all the way to the right. So we started with nx equal to, I think, E3, right? Yeah, and then we got E2, and then E1. I started with this, but then once you solve this, you get that nx square of it, of E3, is 0, right? Why? If you remember. Yes. Yeah. So this guy is in the kernel. So x is in the kernel n squared. Okay. All right. Good. All right. So you call. How do you say it? Then you can write x. Let's finish it first, and then we'll do it. Okay, so we did this. Then we got a solution from this, E1 or E2, and we set this to be 0. So you solve it, and then once again, when you square them, this guy is also right. So here you plug in this. No, you plug in this because then you have nx squared is equal to n squared E2. Okay, which is 0. Once again. All right. Yeah. Okay. Or E3. What am I doing? Just give me a second. N E2 is equal to E3, right? So it's like this. And then you have to take one more power. Then you take N3 x is equal to ne3, which is 0. So then you get that x is in the kernel of n cubed. Is that okay? Does that make sense? All right, good. Then you play the game, but this is the whole space, right? So this is the whole space. No, this is because the nilpotency was n3, right? Okay, so then. What are you talking about? I'm saying that the space is R6, but the kernel of n3 is the whole space, because that's the nilpotency. Okay. No, I'm not done with the basis. Yeah, I have a lot more to do. So one guy in there was E1, and then you play this game again, E1, and at some point I will have to stop it. So NX is E1, or yeah, E1, right? What did we do here? We solved NX equal E2, and I got E1. Right. So I can only do it 2 times. Because if you do this again, so suppose you try to do, yeah, let me do it one more time. So if you play this game again, what happens? So you have 0, x1, x2, 0, x4, 0, equal to 1, 0, 0, 0, 0. But this is false. Understand? So it tells you, so as you keep playing this game, eventually you will get either a contradiction or you will get the 0 vector, which is again a contradiction because we want the basis element. So that means you have to terminate, you stop here. You understand? So it's a very easy game once you get used to it, but that's the only game. So that means your cycle stopped. So you cannot go further. And you only got two elements from here. So let me explain. So the cycle goes backwards, which is very bizarre. So yeah, give me a second. So E3 is the top guy. So so yeah, E3. Okay, so you start with your first cycle, the biggest cycle. I don't know, the big cycle of size 2. It has 3 elements. So let me say this. So the first guy is E3. Then you computed NX of E3, which gave you E2, right? And then you computed NX of E2, which gave you E1. Right? Okay. Now let me get you the one that you want. I will have to write them backwards. I wrote them the wrong way. But so they will only be in terms of, I want to bring the n powers now. So n of E2 is E3, and n squared of E1 is E3, right? Because from here we have this. So we have this, which is this. Is that okay? All right. So let me say it this way. Just want to say. So here you put n squared E1, then you put n E1, and then you put E1. Okay, so I will do this again just to make sure you understood how we did this. And this will be the V1, this will be the n V1, and this will be the n squared V1. Okay, so let me explain again. I will clean this up and redo it, just to make sure we're on the same page. Okay. You start with finding the basis vectors for the kernel of n. One of them was E3. Okay? We will play this game again, but for now, E3. Then you solve the system of nx equal to E3. This gave you x E2. Okay? Good. And n of E2 satisfies it. N of E2 is equal, n squared of E2 is equal to n E3. Okay? The same, so that's one of them. And then you solve this system again, nx equal to E2. This gave you the solution x E1. And we did it again, nx equal E1 gave contradiction. So you terminate at the third step. All right, so you stop your cycle because it doesn't go any further. Good. Now, we don't want it in this form. You have to write it in this power form. So let me explain how we get the power form. Now you play the game in reverse. You start with E1, and n of E1 is what? E2. N squared of E1 is what? N E2, which is E3. Right? Is that okay? So that's how you do it. You find the basis vectors, you start with one of them, you keep solving these systems till you get contradiction or zero vector. And then you say, okay, I stop. I stop right here at E1. Then I go backwards and I have E1, and I have n of E1 and s squared of E1 all the way to nk minus 1, where k is the nilpotent integral. Okay, so that's the game. That's the game we play here. Okay, I'll do it again for the next vector. All right, so the other vector in the kernel was E5. Okay, so let's do this again for the next cycle. All right, so again, E5 is in the kernel of n. Step 2, solve nx equal to E5. So let me do that. So you have 0x1, x2, 0, x4, 0 equal to 0, 0, 0, 0, 1, 0. So who is equal to 1? You can do with your fingers. Good. So x4 is 1, x1 is dead, x2 is dead, x5 and x6 can be any number, same with x3. You pick it, you pick one element, you just need one element that is different from the one before. So take this guy, E4, and play this game again. Solve nx equal to E4. Okay, so let's do that again. So you have 0, x1, x2, 0, x4, 0 equal to 0, 0, 0, 0, 1, 0, 0. Does this system make sense? So you terminate right there, and you form a cycle of only one, of two elements, right? Because we got a solution. So you write E5, E4, and then this guy is equal to NE4, E4. Okay, good. Finally, I think the other guy was N6, right? I mean E6. So let's play this game one last time. E6 is in the kernel of n, and solve nx equal to E6. So this is 0, x1, x2, 0, x4, 0 equal to 0, blah, 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 0, 1. Does this have a solution? No. Contradiction. So you terminate and you have a single cycle of just E6. Okay. So in summary, I'll go back over here. Let me clean this up. Actually, you might need this. Okay. So I'll do it. Maybe move this. So we have n squared. What was it? E1, yeah. E1, n E1, E1, union. I don't have like photographic memory. So we had E5, and then that gave us E4, right? I think it was E4. Yeah. Then we have n of E4, and finally E6. Okay, so that's the basis for the Nilpotent map. All right. So when they ask you to write down the Jordan form for a Nilpotent map, you go from higher order to higher length to lower length. So this is 3 elements. So you have 3 by 3. Next guy is 2, and then 1 guy. Okay, and the way you do it is you put zeros in the diagonal, and you put 1 above each element of the diagonal. Okay, so I mean, we'll do more examples. So let me explain. So we have 0, 0, 0. Let me do with 4. And then you put 1 above each diagonal entry. And that's it. You can just write that. You understand? And okay, let me explain how you get this. I explained it last time, but let me do it again. So the first 3 columns here are given by evaluating over this basis. So you have, so let me do it here. So the first column is n of n squared E1, which is what? Yeah, so this is n cubed, because that's the nilpotency. And then the next guy is n of n E1, which is just n squared E1, which is the first entry. So that's why on the first row, you have to put a 1. And then you do it for this guy. Oh no, sorry, this guy, you have n of E1, which is n of E1, which is the second entry. So you put, I should put it a little bit cleaner. It's the second row. Okay, this is first row, second row. Okay. Is that okay? All right. So that's how you form the block matrix. Okay. We'll do more examples. So if you have a question, just tell me. I can. Okay. And for this guy, you also have what is called a tableau. You will see it in problem 5. So let me clean this up. So here, it's not very hard. Once you have the basis, you just put it in a table like this, without even the symbols. You can just put the boxes. Okay, and I want to do some examples with this, drawing these boxes. Okay, so I gave you the vectors, so we talked about that stuff. So here's some general results. So the total number of boxes in that picture, if you count it, let me go, it's over there, is 6, which is the dimension of V, okay? And So how would you see this? Well, because this is a basis. I mean, we will prove this. It's kind of a stupid thing. So this is a non-trivial fact that these guys are linearly independent. These elements. Yeah, we didn't talk about. I think we talked about it. So these guys are linearly independent, and then we're going to show today and Monday that they are a basis. The cycles. That when they terminate for a good reason, and you still manage to cover the whole space. So we will prove this. This is a result. It's not obvious from the picture. Okay? That these cycles are a basis. So this requires, it's a theorem. All right. The number of boxes in the first row is the degree of nilpotent. And that's because of how we picked the ordering, right? We had, over here, we had V1 and V1 and square V1. So K is 3, which is the nilpotency. What should I say here? I mean, again, this is part of the theorem that we start all the way up to the nilpotency and then we build it down. So we'll go over this. I'm just giving you facts that you can use, okay? You can just say, first row has that many boxes, you know, yes. Yes, yeah. And that's important, not just for the boxes, also for your Jordan form, so that you will have upper triangle. I mean, you could mix it up, of course, but the canonical Jordan form is the one where they're ordered with big, less big, small. Yeah, that's called the canonical. All right. So yeah, I'm just listing the facts that you should be able to, that you're allowed to use freely. Okay, from class we did this, from class we, because they all follow from the basis theorem that we can prove. Yeah, first row is degree of potency, and then we order them in decreasing length. Okay. What else? Right. So the dimension of boxes in the first column is the dimension of the kernel. So let me go up to my picture again. I'll do it here. So we had n squared v1, n v2, and v3, right? Right? That was our picture. And the claim is that the number of boxes here is equal to a dim kernel of n. Okay? And I mean, in a way, this is again in a theorem, but the way you can see it is that we were not allowed to go any further. So, I mean, the first whole row is easy because n cube of v1 is 0. So this is easy. So n cube v1 is kernel of n. Next guy, n square v2. When we tried to solve this, we had some, we had some element here. We got a contradiction. So the only solution was that this is 0. So, okay, let me go a little bit on top to explain what it is. So I will take you back to the contradiction. So where is it? What was all that madness? Yeah, so we were here and we tried to solve the system nx equal to e4, and we got a contradiction. So the only solution, it has no solution. So, and where is it? So we have, so this guy is NE4, E4, and you can check it here. So I'll do it here just to convince you that NE4 would be 0. So, let's see. So we have n of 0, x1, x2, 0, x4. Let me write it this way. x1, x2, 0, x4, 0. And if you act on it again, it will send it to the 0 vector. Okay, because the so if it acts again, you get. So what do I want to say here? So if it acts again, kills this, and this case x1. All right. And what was the point here? The point was, what time was it? I'm overkilling it. The point was you were not allowed to go any further. So yeah, so there is no solution to, yeah, I'm overkilling it. There was no solution to n squared x, okay? That was all I wanted to say, and I don't know where so there was no solution to this. So n of v2 was the maximum non-zero element. Let me just say it this way. I think this is overkill. All right. And again, for nv3 equal to x, there was no solution. Right? We have no solution to this. So again, we have to stop. All right. All right. What else do I want to talk about? Yeah, so here I justify why the dimension of the kernel are the first 3 boxes. And that was because you precisely picked the first entry to be the eigenvector. So I know this is a very bizarre thing, but it's very annoying, but you will get used to it. So in this cycle, the very first entry was our basis or our eigenvector. Okay, we had we generated 3 vectors, right? Where were they? E3, E5, E6. Yes. And let me clean this up and explain. Okay. So E6 is in the kernel, right? And we had n of E6 is 0 because it's in the kernel. N of V1, n squared of V1 was E3, right? That's how we obtained E1. But n of V3 is again 0 because it's in the kernel, right? And then n of E4 was E5. So n squared of E5 is also 0, okay? Because E5 is in the kernel. So we drew this picture so that the first column here, so this was E3, this was E5, and this was E6. So that if you act one more time, they're all dead. So if it helps you put 0, 0, 0 here, okay? I mean, that's always the case, regardless of the length. I mean, you can have a million boxes here. That's irrelevant. All I'm trying to tell you is that the first column is always all the kernel, or the basis of the kernel. Because that's how you form your cycle. You always start from the kernel of n, from the eigenvectors. Is that okay? So when people write in the homework, dimension of kernel is 1 or 2, it would just be like 1 row or 2 rows or 3 rows. Do you understand? Okay. Good. I know we're doing a lot of examples, but I mean, that will show up. So I'm going to show you. Okay, so the reason the first column is always this is because that's how we build our basis. In the theorem and everywhere, even in examples, you find kernel of n, and then you build your cycle backwards. Okay, here's another result. We're going to prove it now. That if you look at 2 columns, so the jth column, and you want to know how many boxes there are in the box, you simply compute the dimension of the kernel of nj and the one just before it. Okay, so let me go to the example again, and I will do it. I will do an abstract proof, but first I want to. So suppose you want to know that indeed you have 2 boxes here. Okay, so what would you do? You have dimension of kernel of n squared minus, can I not write dim all the time? Just put absolute value. So this minus kernel of n. And so usually we will give you some of these numbers. You don't have to do it yourself. But let me see. What should I tell you? Yeah, I mean, I don't know what I'm trying to tell you here. So I suppose I will have to compute this separately. So we already got this to be 3. So I have to find the kernel of n squared. Okay. So let me do that. So n squared of x1, x6 equal to 0. So if you do it once, you got x1, x2, 0, x4, 0, right? We've done this a couple of times by now. But if you do it again, you get what? X1 is dead. X1 came here, and this guy is, so everybody else is 0. So that means that x1 is 0, and everybody else is a real number, but there's 5 of them. So kernel of n squared is 5. Kernel of n is 3. So the number of boxes will be 2. Okay. So that's how you do it in practice. Well, let me prove you that this is always true. So let's do that. This is a book, result in a book. So good, let's do it. So you look at your box, and so let's look at the 2 columns. So the jth column, and so this guy goes from v1 all the way to n j minus 1 v1. Let me make this bigger. All right. And because you know the first row is the nilpotency degree, and you know you have a line. So by linear independence, we claim this result. So why is that? Because they're all linearly independent. So, and we have the following result in general. So consider the space kernel of nj, take away kernel of nj minus 1. Okay, this is a space. You just subtract. Okay, so these are all the elements where nj of v is 0, but nj minus 1 of v is not 0. Is that okay? This is a subspace. You can prove it. Yeah. So you can prove that. I mean, unless they ask you, but I don't think so. But yeah, this is a subspace, and this is a column of Li. Okay. The reason you only have inequality and not equality is because in general the size of Li is less or equal than the dimension of U. If you also have that it expands it, then you have Li is equal to d mu. But you don't have that. All you know so far is that these guys are linearly independent. Is that okay? Right. So that's how you get the inequality. Now let's get the equality. We will prove this theorem that the total number of boxes is dim B. Okay? We will prove this. I mean, that's how it is. So, so you have two things. Okay, I mean, this is a bit confusing the way I'm saying it. So by basis theorem, we have total number of boxes as is dim B. Okay. On the other hand, this is a telescoping sum. So let me write it down. Yeah, it's a very dirty trick. So this is the number of boxes. And let's do it. Let me get you the first, let me get you this. So you have a dim kernel of n2 minus no more dims. So this minus this, kernel of n cubed minus kernel of n squared, and so on. And yeah, you should start from kernel of n. So you go all the way down to kernel of n cubed, which is over here, because no, the nilpotency. Yeah, we're doing general result here. I'm not talking. So the nilpotency, whatever the nilpotency is, kernel of nk minus 1. And this is a telescoping sum. So this is equal to kernel of nk, right? But this is a dim B because of k is the nilpotency. Is that okay? So that's how you get star. We will prove this called the base theorem on Monday. Okay. And then, I don't know if you can get it from here, but let me put them together and see if you can get it. So column of J is less than kernel of Nj minus kernel of Nj minus 1. And you also have that the summation of columns is dim V, which is also equal to this difference of kernels. Can you get from here that in fact you have column of J equal to this dim of the difference? It's just an algebraic trick. I want to see if you can do it. How would you do it mathematically? You know their sum is equal to the same number and their positive entries. That's a way to get it. Just a small trick, just to make sure you're suspect. Huh? Okay, good. I think you got it. So you mean like there is some j. Perfect. Is that what you? Okay, let me. Yeah, you say it. Sorry. Oh, right, but I want to prove equal, that they're equal. Yeah, but I want to use these two facts to get that I have equal. Okay, I mean, it's simple. So let me say, it's by contradiction. Suppose there was one guy that goes the other way. Okay, so suppose that you have some J star, so that the column of J star is bigger than, 1 plus this guy, call it DJ. Okay, so there's at least one. And just take the differences. So you have summation of column J is equal to n summation of the DJs, right? Subtract them, and so what do I want to say? Right. So this guy is bigger than summation of the column J. Let me get it. And so what do I want to say? So we have one of them, call it D1 because I'm tired. It doesn't matter. So, oh, okay, I see, never mind. So you cannot have greater, you can only have, this is very annoying. So this guy is bigger than 1 plus column of J star. So I want to say that, I want to do it the other way. Sorry. I want to say that this guy, that DJ star, is equal to column, is strictly bigger, yes. So it's bigger or equal to column of J star plus 1. Is that okay? Huh? Is that okay? Because you want them to be equal. You already know it's bigger than it, but I'm saying add a little buffer. But here's the problem. One of them will be bigger than column of J star plus 1. But this is equal to n plus 1. So you get that n is bigger or equal than n plus 1. Is that okay? Okay, all right. We'll continue Monday, Tuesday. No. I have an idea. Tuesday? Any questions?